In the last video, we learned how to describe spaces with vectors. However, things could get really confusing since there were so many vectors involved. In this video, we will learn how to describe entire spaces with only a few vectors. This video is a part of From Zero to Geo, a series where we formulate geometric algebra, an incredibly powerful branch of mathematics, from the ground up. So how can we describe an entire space with only a few vectors? Let's look at the plane and pick some vector. Because this vector moves along the x-axis and is a unit vector, let's call this vector x hat. Remember that the hat on the letter means that this is a unit vector. What vectors can we reach from just this one vector? Well, with just one vector, all we can do is scale it. So the only point we can reach with x hat is just the x-axis. So just x hat by itself is not enough to reach the entire plane. Let's try bringing in another vector. Because this vector is a unit vector along the y-axis, let's call this vector y hat. What vectors can we create with both x hat and y hat? Well, we can scale both of them like before, but now we can also add them. Come to think of it, we could also scale x and y before adding them, allowing us to reach many more vectors. Just how many vectors can we reach with a combination of x hat and y hat? To be more precise, what vectors are of the form ax hat plus by hat? Another important related question is what vectors are not of this form. See if you can answer all of these questions. To try to answer these questions, let's pick some random vectors and see if we can write them as a combination of x hat and y hat. Let's start with this vector. Can we write it as a combination of x hat and y hat? What's nice about x hat and y hat is that one is purely horizontal and the other is purely vertical. Thus, we can consider the horizontal and vertical parts separately. For the horizontal part, notice that v goes 2 units to the right. Thus, we are going to want to set a equal to 2. Similarly, v goes 3 units up, so we want to set b equal to 3. We see now that v is equal to 2x hat plus 3y hat, so yes, v can be written as a combination of x hat and y hat. Let's do another one. What about this vector? We can see that v only goes 1 unit up, so y hat doesn't need to be scaled. Thus, b is 1. Now, x hat points to the right, but v points to the left. So to reach v, we need to scale x hat by a negative value. v goes 4 units to the left, so we need to set a to -4. So we see here that v is equal to -4 times x hat plus y hat. Let's do one more. What about this vector? This one doesn't go right or left at all. How do we deal with this? Because we don't want to use x hat in this case, we will just set a to 0. At this point, all we need to do is scale y hat by -3. Notice that in general, the coefficients of x hat and y hat are precisely the coordinates of the endpoint of the vector we are trying to reach. This shows that we can write any vector on the plane as some combination of x hat and y hat. Now, if we move to 3 dimensions, we can see that we can't reach any of the vectors that are not on the plane. However, if we add another vector, like this one, we could then reach any vector in space. Because it's a bit hard to think about adding several 3-dimensional vectors, I'm going to avoid talking about it for the moment, but it is important to keep this situation in mind. Now, in this case, it was pretty easy to write a vector in terms of x hat and y hat because x hat and y hat are perpendicular. Let's try something a bit harder. What about these 2 vectors? What vectors can we reach from these 2? For instance, try to make this vector from u and v. This one is quite a bit harder than the previous ones, but you should still try to figure it out for yourself. There are many ways you could solve this. In the end, it turns out that w is -3 times u minus 2 times v. The way you figure this out isn't important for now. To be honest, when solving this myself, I just eyeballed it. The important thing is that it was possible. While I'm not going to prove it, It turns out that it's possible to represent any vector in the plane as a combination of u and v, just like before. Let's do one more of these. How about these vectors? What vectors can we reach from these two vectors? See if you can write this vector as some combination of u and v. Try to figure this out before continuing. Now at this point, after trying to solve this, you might be angry with me because it turns out that this one is actually impossible. No matter what values you pick for a and b, you can't escape this line. However, you can still reach vectors that are on this line. There are several things that we can learn from this discussion. First, what we have been doing is taking some vectors, scaling them, and then adding them together. We're going to be seeing this way of combining vectors frequently, so we should give it a name. Because it looks vaguely like the equation for a line, we will call this kind of combination a linear combination. We sometimes want to combine an arbitrary number of vectors together in the same way. When we have this situation, we still call it a linear combination. Linear combinations are incredibly important, so it is important to become familiar with them. Notice that before, when we were trying to write vectors in the plane in terms of two vectors such as x hat and y hat, what we were really doing was asking which of the vectors in the plane could be written as a linear combination of x hat and y hat. This idea of asking what vectors are a linear combination of some other vectors leads us to another idea. Notice that we can rephrase what we have been doing as asking what vectors are a linear combination of vectors in the set that contains just x hat and y hat. Instead of just thinking about x hat and y hat, we could start thinking about an arbitrary set of vectors and asking what vectors are a linear combination of vectors in that set. This concept is important enough to give it a name as well. We call the vectors that can be written as a linear combination of vectors in a set the span of that set. Notice that when we take the span of a set of vectors, we get another set of vectors in return. To get a better feel for spans, let's go back to what we were doing earlier and describe it in terms of spans. With just x hat, the only linear combinations of x hat are the scalar multiples of x hat, which ends up forming the x-axis, so the span of just x hat is the x-axis. With both x hat and y hat, we found that many more vectors could be written as a linear combination of x hat and y hat. In fact, as we saw earlier, any vector on the plane can be written as a linear combination of x hat and y hat, so the span of x hat and y hat is the xy plane. In 3 dimensions, we found that any point in 3D space can be written as a linear combination of x hat, y hat, and z hat. Thus, the span of x hat, y hat, and z hat is all of 3-dimensional space. When we went back to 2 dimensions with these two vectors, we found that the span is again the xy plane, and when we considered these two vectors, we found that the span is just this line. You might be noticing a pattern here. In each of these examples, the span of a set of vectors was either a line, a plane, or 3D space. These are all spaces. This leads us to a natural question. Is the span of a set of vectors always a space? To answer this, we need to remember the condition for a set to be a space from the previous video. Let's say we have a set S of vectors. To see if the span of S is a space, we need to see if adding 2 vectors in the span is still in the span, and if scaling any vector in the span is still in the span. Let's check the adding condition first. To determine if this is true, we need to figure out what the vectors in the span of S even look like. Because the span of S is all possible linear combinations of vectors in S, a vector in the span of S is a linear combination of vectors in S. Since we need 2 vectors in the span of S, we need another linear combination of vectors in S. Now that we have 2 vectors in the span of S, we need to add them and see if the sum is still in the span of S. To do this, we can rearrange the sum and then factor out each of the v's. At this point, notice that we have the vectors in S, each of them is multiplied by a scalar, and then the results are added together. This is a linear combination of vectors in S. Thus, this vector is in the span of S, showing that adding 2 vectors in the span of S is still in the span of S. Let's now see if scaling a vector in the span of S is still in the span of S. Like before, we need to pick some vector that is in the span of S. Now we need to scale it by some value and see if this new vector is in the span of S. To do this, we can just distribute. Like before, we have the vectors in S, each of them is multiplied by a scalar, and then the results are added together. So we again have a linear combination of vectors in S, showing that this vector is in the span of S. Thus, scaling a vector in the span of S is still in the span of S. Because adding vectors in the span of S stays in the span of S, and scaling vectors in the span of S stays in the span of S, the span of S is always the space. So in light of all of this, let's go back to our initial problem. How can we describe all of the vectors in a space with just a few vectors? All we need to do is find a few vectors in the space that span the whole space. When we have found a set that spans a space, we say that the set is a spanning set for that space. However, it seems that some spanning sets are better than others. For example, this set of vectors does span the plane, but it would be more confusing to use this set as our spanning set than some of the other sets we have looked at in this video. How do we find a good spanning set? We'll answer that in the next video.